So in this video we'll be diving in the Euclidean geometry. Okay, we all know that Euclidean geometry is a math, obviously, and that works with angles, shapes, and as you go with it, also includes shapes like circles. But earlier grades all about lines, triangles, of which were simpler to work with. So our course, please bear with me, it's going to be a very long course. It's all about that. So as soon as you finish, I promise you'll be all fine with Euclidean geometry. Most students which they find challenging, when you'll be all just fine, trust me. So if I have to talk about Euclidean geometry, it goes back to grade 7, if I'm not mistaken. They gave you a problem like this one, and they gave you a let me just say alpha. Let me just use A for now. And then they gave you another angle here, and they said this angle was 120. And the question was, for 5 marks, just give us angle A. And you were like, oh, I don't know what to do. But you remembered something very important. They told you again in the very same grade, they told you that sum of angles along the line, like all the angles along the line, should sum up to 180. So you know that 120 plus our angle A should give us 180 degrees. And you also have to say reason. The reason is angles in a straight line. You should write the full with the 1 marks, right? And then you're going to solve for A, and then you have A, and you isolate A by taking 120 to the other side. You'll have 120 minus 180 degrees. What am I trying to say? But you see it, okay? And don't forget that your teacher will penalize you for not seeing these degrees, okay? Make sure that they are there. Okay, so if I try to find the difference in these two numbers, I don't know the answer. You do, right? Just tell me that. I heard you whispering somewhere there. You whispering something like 60 degrees. Oh, we just got number 60 degrees as the angle. Yeah, okay, we know 60 is a very important number. It's one of the special angles. It's special, okay? And I'll now go back to I'll just run to a triangle within 60 here and 60 here, and they call this one B. And now they say give us B. This is Euclidean geometry. Remember, we're trying to build a foundation. Okay, you was going to say 60 plus 60 degrees, remember, plus B should give me 120. Oh, what a coincidence. That's the same as this one. That means if you can add all the angles here, they're going to form a straight line. Okay, you're not going to worry about that, but think about it. Okay, and you take this, put it here. And what we were trying to say, we are saying because of the sum, okay, let me just write sum of angles in a triangle add up to 180. Okay, so now we can get these 102 60s. They give me 120 plus B is equals to 180 degrees. Remember, don't make that mistake. And you'll have B, and you have 180 degrees. You take this to the other side, then it's going to be negative. It's going to be 120 degrees, and again you get an angle called 60 degrees. Oh, okay, you keep getting 60 degrees. Okay, so I'm not saying that in your test you're going to get this 60 degrees. I just made up these problems intentionally to get this 60 degrees. So I'm trying to emphasize that there is a triangle, or there exists a triangle that all the sides, not all the side, all the angles inside equals to 60, and that triangle is called an equilateral triangle, right? A triangle which all sides are equal. So we just learned something that there is a shape called an equilateral triangle. Let me just write, it's always denoted like this, and this shape has angle 60 in, it has an angle 66 inside, and all angles are 60, and if you sum them up, obviously you get what? 180. Okay, we just got something very important for our Euclidean geometry. Okay, this is not all what we're going to need. I'm going to go back to your grade 7 again, I hope, and there was something like this and this, and you were given an angle here called 45, and they said give us an angle, or let me call it alpha. Okay, I'm trying to put alpha now. Okay, so you are going to say this was the easy one. Whenever you see a cross, angle on this side, angle on this side should be the same, and angle on this side should be the same as angle on this side, given that these lines are straight lines. Okay, because they might be connecting like this, but they are on bends to this side, so you can't say this is equal to this. This should be a straight line, as this is a straight line. Then you can use you can now say alpha is equal to 45, remember what I said, degrees, is equal to this one. The reason it's vertical opposite angles. Okay, so we've learned that there is a reason called vertical opposite. If you see a pirate, X. If you see an X, vertical opposite. And if you see something else called and then if the angles are on the straight line, you can sum the 280. And also if the angles are in the triangle, why are you not coming up? Triangle, yeah, if angles are in the triangle, if A, B, C, that means that A, okay, let me rewrite them in a very nice way. A, B, C, that means A plus B plus C should equal to 180 degrees. The reason is sum of angles in a triangle, they sum 280. Okay, hope you're following. We've accumulated very important information on our way. Okay, and also there's something called parallel lines. Oh, okay, I just drew parallel lines, trying to underline parallel lines. Okay, they are denoted by this symbol. Parallel lines, we are told in early grades, that are lines that never meet in an Euclidean geometry. In other field of geometry, as you grow old with your maths, you'll find them meeting. Okay, but for now, like in a circle, in a sphere, they meet, but for now, just get it. Parallel lines don't meet, and they have an equal space in between. If they were on the Cartesian plane, parallel lines will have same gradient. We're not worried about that for now. It's not part of our curriculum. Okay, not part of our course. Okay, but we just know that parallel lines never meet. Okay, there is a lot of Euclidean geometry in parallel lines, and we call this a very fun geometry. This is fun geometry. It's fun, just fun geometry in parallel lines. Okay, I'm going to rewrite the fun geometry for you so that you see exactly what I mean when I say it's fun, because it is really fun. It is really fun, right? I'll just try to show you why I'm saying it's fun, and you'll just see it fun. It really is fun. I hope it is fun to me as much as it is fun to you, as much as it is fun to me, because I really think this is fun geometry of parallel lines. Okay, given that this line is parallel to this line, and this line is parallel to this line, and this line is parallel to this line, hope you saw this line are parallel. Even if you think, or maybe your eyes are trying to lie to you and telling these lines are not parallel, they are parallel. Okay, believe me, they are parallel. Your eyes are lying to you right now. These lines are parallel. If you see them translating, you are just trust me, okay, over your eyes. Okay, if these lines are parallel, that means the angle here should be equal to the angle here, and we call that one corresponding angles. Corresponding angles are equal given that if a line cuts through parallel lines, it will form corresponding angles that are equal. Also here. Okay, that was F for fun. Okay, F for fun, corresponding angles. You got that right? I trust you. And also there is U for fun. U for fun. Yeah, you watching the video for fun. Okay, there are co-interior angles. Co-interior angles are angles within the parallel lines. Let me say there is a parallel lines and there is a line passing cutting through those parallel lines. The angles inside should sum up to 180. They call them co-interior angles should equal to 180. They sum to 180 just because they are just a half of a quadrilateral. You will talk about that later, but for now just get it. They just sum up to 180 co-interior angles. Okay, and this is just your very low grade geometry, Euclidean geometry. I'm trying to build up a very firm foundation before I go into and those advanced cyclic geometry theorems, and you'll be like, I can recognize this, okay, because we're going to make use of a lot of this information in our high and advanced geometry. Okay, even in engineering they just use the same fun geometry, just that it's kind of get complicated sometimes, but if you did understand this, you'll be fine. Okay, so now Z fun, the last one is Z. Okay, how did I say that now? It's fun, the last one is Z. I don't know how, but I think I was looking at it at an angle, but the last one is Z. Z, they call them alternating angles. Alternating angles are known to be equal. In this case, it's fun for N, but normally I prefer calling it Z for some reason because it really looks like Z. So if you have, again, parallel line and there is a line passing through and you can see a Z forming, and always this is going to be equals to this, given that this is parallel to this. So now you are ready to tackle the real geometry? No, not yet. Okay, one more last thing. Okay, also in Euclidean geometry you'll need to have a lot of information about your shapes, of which are your squares, your triangles, I think those two are very important. Let me not say square, let me say quadrilaterals and the rest of the shapes. But okay, there is this shape that it is a very strong shape out of all shapes. Okay, I don't want to say why, but it is one of the most strong shapes we have. I didn't want that. Okay, it is one of the strong shapes. It's used in, if you can see, most of your structures have these triangles. They call them triangulations. I think you did that in your early technology, and if you follow your path into engineering, you'll see most of these shapes, they are used because they are very rigid shapes. Okay, and they have very fun geometry inside. Okay, we all know this, that's this angle plus this angle plus this angle is equal to what? Let me call it A, let me call this B, let me call this one C. In the early we said that A plus B plus C should give us 180, given that this is a closed triangle, and we say there is a sum of interior angles of a triangle. Okay, that is our reason. Do you see blue? Hope you do. Okay, I'll never use it again, I promise. Okay, but we also know that, let me call this one D. We also know that sum of angles around a straight line should give us what? Should give us 180 again. That implies that C plus D should give me 180. The reason it's angles in a straight line, right? In math, you have every right to write something that doesn't look like it should, but as long as a teacher will be like angles in a straight, like I know what he's saying. Okay, they are very not straight when it comes to language and everything, because this is math. Okay, it's a language on its own, so you don't need your English for now. Okay, where we are now. Okay, we just discovered or recognized something that we just did before: angles in a straight line and angles in a straight line just here. So now we are happy mathematicians, are we? Yes, we are. Okay, then now, okay, let me try to make this thing not too complicated. But we also know something, that this angle here, B, A, and angle B, if you sum them up, they should give you an other angle. This has its name in mathematics. They say this is A plus B should give us D, and they say opposite interior angles of a triangle equals to exterior angle. Okay, they just say two opposite angles inside the triangle are going to give you the outside angle. It's always like that. Okay, it always. Okay, maybe if they extend the line here, that means this plus this will give me this. Okay, I hate that. I just ruined my drawing. But you get the point, right? Wherever, as long as there's an extended line out of a triangle, two opposite interior angles will sum up to the out triangle. Okay, this always helps out if you're working with geometry. Most of the time, if you're missing an angle, it should be this guy. You'll be like, I don't see him, he's always hiding. It's always him. Even on circles, he hides there. Make sure you find him, okay? Okay, why is this so? Okay, but should I do this? Yes, I think I should. Okay, hope I don't complicate people's life as mathematicians do. Okay, that's our responsibilities as math teachers, to make life very hard for you guys. Okay, that's not mine. Okay, but it's just perks of teaching math. That's how it is. What I was trying to clear out here, I was trying to say this angle is equal to, let me remove this, the green angle and this green angle give me the big green angle outside. That's what they say. Sum of opposite interior angles equals to exterior. Okay, hope now you see it. This is true because this plus this misses this angle to make it 180, of which let me call this B, and we're saying the outer angle is A plus B. So also again here, if I look at in terms of a straight line, A plus B misses some angle C to make it 180, as much as A plus B misses C to make it 180 inside the triangle, this 180 in the line. So can you see now the relationship between a straight line and a triangle? They are very related. They just have same angles inside. Okay, so now you'll be like, this teacher just wasted 20 minutes trying to get me understand primary Euclidean geometry. I did this because I was coming to the very fun again. Relax, it's getting more fun, and fun is more we dive into math. This is the shape. Okay, how many sides in a shape here? Let me try to count. I don't. Okay, I literally don't. I don't know how many sides are here. Okay, who cares? It's a circle, by the way. It's called a circle. This is the name of the shape. For those who didn't know it, it's a circle. I just made you there. You know a new shape now. Circle. Circles are known to have a center, O. I just named it O, not like it's always O, but mathematicians love O. It's always O, not always. Most likely it is O. Okay, and there is this shape has a perimeter. What is perimeter? Remember in primary they were like, perimeter is a distance right around the shape. We all sang that, right? So it's the perimeter for a circle is called circumference, right? Circumference. That is a distance right around the shape, specifically a circle. So that's good. We know something of a circle now. And a circle has something called diameter. Okay? Diameter. Okay, I'm very bad in this writing thing. The diameter. Oh, now it's better. A diameter is a line that passes through the center to the circumference of from the circumference to the center to the circumference, and it's a straight line, and that is called what? A diameter. Okay, but we also know that our diameter is made up of, it has two components, right? Let me just say D for diameter is equals to two components called R plus R. What is R plus R now? New terms, okay? Obviously it's not new terms, trust me. We call these ones radius, and it's a radius. It's from the center to the circumference. So two of these are going to make you what? A diameter, obviously. You know that. So now you are almost there with your maths, okay? You're almost there. Diameter to radius make two radius make a diameter. You know that now. And this one is not too important, but it is here. It is too important for circular geometry. Okay. This what I just drew there. It's what is called a chord. Okay, that is just a chord. Okay, and on the other side, this area here, I can't really use this area here. If you see it, it's not too important here because we're not so interested in the areas, but I tried to write it here. It is called a segment, right? Segment. Okay, and we also have something here. Let me remove this and this. We have something here. This is called a sector. In your pie charts, you see most of these. This is a sector. Whatever I'm going to highlight here, it's also an area. So don't worry about areas for now. Okay, but it is there. I just want you to know it. I don't want you to say I hide something from you. I'm giving you everything you need to know, right? This is a sector. Okay, so a sector is just a piece of pizza. Okay, it's just a sector, and this one is just some small piece. I don't know what you call it. Like I don't have a literal meaning for it, but this one is a pizza slice, and this one is just a corner pizza slice. If somebody just don't want to give you their pizzas, they're going to cut you a segment. But if they do want to give you, they'll give you something called a sector. Okay, so all these terms, you're going to find them going on and on again in your geometry. Make sure that you have an idea in them. Okay, let me just one more thing. Okay, there is also something. Oh no, I didn't want it to be like that. Something like this. No, I want it to be like that. You're supposed to touch once. Okay, you know what they call you? They call you a tangent. A tangent is a line that touches once, or that touches a circle once. You can see it in functions. They use the same tangent, because it's all about touching the circle once, or maybe the function as a more of a function. Okay, mostly wave functions and on all the curve function, they have a tangent. Okay, and there's also a line from here to here, and this line is called let me give it a name. You should know it. I told you, right? I call this one a radius. Okay, and the radius, whenever a radius meets the tangent, it's always going to form something 90 degrees. Okay, my angles are coming in again. It's going to form 90 degrees, and this is a theorem. This is one of your theorems that you need to know on your circular geometry or circle geometry, and this is called a tan radi. Okay, I just said it's tan radi. It's tan radi, and it means whenever a tangent meets a radius, it's going to be 90 degrees. Don't forget this again. Please do it for me. Don't. Okay, I really don't want to say this theorem. I just had to talk about because it just has a special line called the tangent, of which it's part of the what do I call it? I was just doing the vocabulary, so I was just building vocabulary, not yet on the theorems. So it's a theorem, yes, but I'm not too focused on it for now. I'm just trying to build your vocabulary so that you start your geometry. I think we can start the geometry now. You are ready, you are equipped with very good geometry vocabulary. So if I bring up some new terms, you'll be like, I can recognize this term. He did say it, right? Okay, so you know what I'm talking about. Circle geometry. That's where I am at. Okay, and I'm going to start with theorem first. Teachers love to say this is theorem first. Literally, you're not required to know who comes first, who comes after, as long as you know them. Okay, they don't need you to know all of these things. Okay, and there is a center here, and this one is called line from the center. From the center, let me call center O, to the chord. You know the chord. I told you what a chord is, right? You remember it. If you forget it, just scroll back on the early times of the video and find this. Okay, so I was supposed to use a perpendicular line here. They are literally saying that there should be a line from here. If a line from here to here, okay, let me just give this thing name so that it will be easy for me to work them with. It's going to be M, P, O. We love giving this O every time. The center is always O. This is M. Okay, so here it is said that this is perpendicular. The line from the center to the chord is perpendicular to the chord. Okay, so this implies that this is equals to, okay, let me just think it about. Okay, I'm right. We're just trying to find that this is equal to that, and to do that we are going to create some shape. Okay, I don't know the name of the shape. You would remind me, hopefully. I did tell you, 3-side shape. They told you it's a triangle. Okay, tri means three angles. So we're trying to prove that we are required to prove that M is equals to MP. Okay, I don't know how we're going to do that. Hope you do. You're going to help me out, right? Okay, so how is that possible? We can do that by proving, we can prove congruency, right? Okay, we did talk about congruency in your lower grades, obviously. Okay, so we know that ON is equals to OP because they are both radii. Okay, they are both radii. Okay, all the radiuses in the circle are equal. If there is a radius here and the radius here, the radius will be equal to this, equal to this, equal to that one, right? All the radius in a circle are equal. So we're using that fact, okay? And it was given that angle PMO is equals to 90. Right, it is given. It's what I told you, that given that you can see it right now. It's given that they're always going to give you if they want you to prove this. Okay, so it's equals to 90. Also, it's also equals to O M N. They normally put a hat on the middle of where the angle is. Okay, so that's good. And we can also state another fact that we know that OM is a common side. Given now we have 3 reasons. Once you have 3 reasons for a triangle, that means those triangles are strictly the same, congruent. Okay, so we can now conclude that triangle OMN is congruent, right? Is congruent to another triangle called OMP, and the reason is that side, right angle, what is missing? Common side again. So this one for radius we call it hypotenuse. The reason is going to be right angle, hypotenuse, side. We just saw it just here. So we just proved that if these triangles are the same, that means therefore MN is going to equal to MP. So now you know. Theorem number 1, given that this is there is a line from the center to the chord and it's make a 90 degrees or yes, let me just say 90 degrees for you guys. 90 degrees, and that implies that these, or that tells us that it's bisects the chord equally. Okay, theorem number 1 also has its converse. This is the word they use. Converse is just the other way around. If they tell you that these lines are equal, that they are trying to tell you that this is also perpendicular. That is the converse of theorem number 1. It's called what? Line from the center perpendicular to the chord, right? So it's the other way around of the first one. So it's this how it works. Okay, they can tell you this is 90, they mean these are equal, or they can tell you these are equal, they are trying to tell you this is 90. So that's how mathematicians are. Now we are on theorem 2. Okay, so this is theorem 2. Theorem 2 states that an angle at the center is equals to 2 angle at the circumference. So it can be any stupid configuration, or there was supposed to be a circle. Okay, it can be any. Okay, so let me say this is the shape. I think I did try. They're saying that this angle in the center should always equal to the angle twice the angle here. It doesn't look pretty good, but it's always like that. So then maybe there is another one. I'll just draw the one that I have on screen. Okay, this is the most easy one. They're saying this, the angle here is always to the angle here. So if this one is x, this is going to be 2x. Okay, that's what theorem 2. Angle in a circumference is equal to, angle in a center is equal to 2 angles in a circumference. This is your reason, wherever you say it. Okay, but this is what I do here. I just say the theorem and I try to prove it for you, because these proofs are examinable, right? They can be asked in your exam. You're just going to come here and revise them, okay, for your exams. But this is a triangle, Okay, another special triangle that I forgot to mention early, it's called an isosceles triangle. An isosceles triangle says that if this, given that these sides are equal, that means that these angles are equal. Or maybe the converse, given that these angles are equal, that implies that these sides are equal. So you know it now, isosceles triangles. Okay, and same angles in the base, that means same sides. Okay, equal side, not same. Equal angles, not same angles. Okay, so I was fixing my vocab there. Maths is its own language, so once you mess the way you said, you just missed it. So we are required, let me just name this thing before, it's C, A, B, C, and I'll always have, I love having O here. I don't know, center look good when it has O. Okay, let me just call this one 1, O1, O2. And I'll call this one C1, C2. Hope you see it very clear. I'm trying my best, okay? So, we are required to prove that AMB, the angle in the center, is equals to the angle in a circumference is equals to 2ACB. Okay, we're trying to prove the theorem itself, right? So how are we going to do that? I don't know. But I can say some few things that maybe they can help you as the math student to see how can you go about the proof. I can say that what I see here, AO is equals to MB, and this is equal to this, and I can say it's also equals to CM, and these are all radii. That's why I'm saying they're equal. So I don't know the proof, but I know this, okay? I'm just saying everything that I know. Hopefully what I know can lead you to what you want to say. Okay, if you come close here, you notice that if this is equals to this, that implies that AOC is an isosceles triangle. If it is an isosceles triangle, that means this is equals to this. So we can state that also. I can say that C2 is supposed to equal to A. The reason angles opposite equal sides. Or you can just say isosceles triangle. I love that reason. It's so easy. I don't like you. The reason it's isosceles triangle. Okay. What else can I say? The isosceles triangle also work here. This is equal to this. I can say OBC is also an isosceles triangle because they are both or all subtended by radies. So I'll have C1 equal, there was C2, right? That was C2. Now I'm on C1. I am C1 equals to B. The reason it's also an isosceles triangle. Okay, that's good. That a good start to have. We are heading the right direction, we hope. And now we can say that O1 is equals to A plus C2. The reason I'm saying, remember this triangle? Hope you do. There was a triangle and there was this, and you said this and this supposed to give us this. Opposite interior equals to, let's just say opposite exterior angles. opposite interior angles equals to an exterior angle. Okay, sometimes they just sum it and saying exterior angle of a triangle. Okay, but we also know, let me just call this O1, right? We also know that we did say this is equal to this. We said that just here. That means I can just make it, I can just say 2C2 because they are the same, right? Also, A is a C, C is a C, so I can just say 2 C's instead. So I have this. Okay, that's good. That's very good to know. I was looking at this triangle. Let me just remove all this to have more room. Okay. So now we know that we can come to the other triangle now. This one is plus this one also give me this one. This look like this. If you're really confused where I'm getting all these numbers, this look like this, and this law, oh, okay, this theorem says that this and this is supposed to give me this. We did talk about this and this supposed to give me this. Okay, opposite interior equals to exterior. Okay, let's not worry about that now. Okay, let me do it. I'm saying O2 is equal to C1 plus B. B plus C1 equals to O2. But we know that C1 and B are the same. We got that here, right? Because of the in the isosceles triangle, right? And we can just call this one 2C1 is equals to O2. Okay. But we notice that angle O is this one, right? Let me say angle O 1 2 just is equals to angle O1 plus angle O2, or I can just call it angle O in the center, okay, or angle in the center that we're talking about. So what is O1? O1, we got it here. We said it's equal to 2C2. What is O2? We said it's equal to 2C1. That is O in the center, right? We can then factor out 2. If we take out 2, here we have 2 remaining. Here we'll have C1 remaining, and we'll have here O1 2, whatever you want to call it. But this angle, to be specific, this angle here. So we just, okay, and also if you come back here, C is equals to C plus C1 plus C2. So this is just C and this is just O. We just discovered a theorem that said angle in the center is equals to 2 angle in a circumference. That we just discovered or proved here. We've proved the theorem. So we move to the next theorem now. So theorem 3 is we don't have to prove this in your grade, okay, but it's obvious. I'm just going to not prove it anyway. Angles in a semicircle. They call it angles in a semicircle. Others call us angles subtended by a diameter. Yeah, they call it everything. Literally, it simply means that if there is a line that goes from here to here, and that line is called, obviously we did talk about this, don't disappoint me, that is called diameter, and then here it's going to be 90. That's what theorem 3 says. That's all. Okay, that's all. And its converse, you always know that these theorems have their converse. The converse is just the other way around. Okay, don't worry about them too much. They just mean the same thing. So they say the converse says if this is 90, then this is a diameter. The theorem said if this is a diameter, then this is 90. So double implication. If this is this, then the other one is the other one. Okay, so don't worry about that. The converse is just the other way.